Okay, so now we're going to go over our summary sheet and an example here for systems that have the objects at rest. So I'm going to be going back and sharing my iPad, actually my daughter's iPad, who's helping me here with these first videos, so thank you. Okay, so at rest. So what do we already know about objects that are at rest? Well, we know that their velocities are equal to 0. We know their acceleration is equal to 0. We know that there is no net force, so that equals 0. And we know that they have balanced forces. We also know from the previous chapter that if you take a position versus time graph or a distance versus time graph, that their position never changes. So you're going to end up with a horizontal line. That horizontal line could be anywhere on that position time graph. It could be farther down. It could be farther up. It really doesn't matter, but it's going to be a horizontal line. The velocity time graph is always going to be sitting on 0. So it's going to be sitting down there on the x-axis, and I try to draw it so you can kind of see that there is a different color there, but it's always on the v equals 0 line. Okay, so let's do an example. We've got the problem of a 20 kilogram box sitting on a floor. And we're going to draw the free body diagram. And we're going to label our forces. We're going to calculate all the forces that we can find, all of our net forces, and any acceleration. So let's go back using our steps from before. So I have out that earlier page that has all of my steps on it. So if you have that still accessible in your packet, which is page 31, you might want to be able to kind of flip back and forth just in case. Okay. So this one, we're going to first identify all the forces that we have. So we have an object sitting on the floor. So it's got F gravity pointing down. We have it sitting on the floor, so it must have a normal force. So F norm pointing up. And that's all that we've got. It's just sitting there on the floor. It's not being pushed. It's not being pulled. It's not moving. So that's all we have. Okay, so what else do we know? Well, we know balanced, so we know those two forces are equal, so there is no acceleration in either the x or the y direction. There's balanced forces in both the x and the y direction, so those both equal 0. All right, so now we can calculate our force of gravity knowing our mass. And I forgot to write the 20 kilograms inside the box. So let's fix that right now. And as long as we're writing kilograms, if you can't kind of fit the kg inside the box, just write 20, which is fine. Okay, so weight equals mass times g. So we've got 20 kilograms times 10 meters per second squared. That's going to give us 200 newtons. So we know the force of gravity is 200 newtons. We know that it's balanced, so the force normal is also 200 newtons. So a couple of things to note. Anytime we have an object at rest, whenever we have an object at rest, you can start out right off the get-go after you read the problem statement that the net forces in both the x and the y, as well as your accelerations, are always going to be 0, okay? Anytime you have an object at rest, those are always 0, and so you don't even have to fill out the forces and finish your free body diagram to have actually filled that bit of information in, which kind of makes it easy because you've already got the information, you can fill it in, and that's already 4 items that you figured out. So that would be 4 points on a problem on something like this. Okay, so let's look at constant velocity. So that will be on the next page in your packet. So for constant velocity, we're on page 33 in your blue packet, and we're going to go out and go do the same thing. So for constant velocity, v is going to be equal to a number, some number. We don't know what the number is, but it's going to be a number. It's going to be the same number all the time. Okay, constant velocity, there's no acceleration. There's 0 net force, and it's still balanced. So if we look at our position versus time, we're going to see that we're going to have a straight sloped line this time. It's not horizontal, and it shouldn't be vertical, but it's going to be having some slope. It could be a positive slope. It could be a negative slope. Our velocities are going to remain constant through all of the time, so they are going to be a straight horizontal line. Again, it could be farther up, it could be farther down, it could be negative. All right, so let's look at our first problem here. We've got a 30 kilogram box being pushed to the right at a constant velocity. It says a 20 Newton force is being applied to move it across the floor. Draw your free body diagrams, label all your forces, calculate all the individual forces, the net forces, accelerations, etc. Okay, so first thing, it's a 30 kilogram box, so let's put 30 inside of our box. And it's being pushed to the right, which tells us that there's an applied force going to the right, so F app. And the other forces that we know is there's going to be gravity going down. There's going to be normal going up because it's going to move across the floor. And since this thing is moving across the floor, there's going to be some amount of friction going to the left. So F fric. And it's going at a constant velocity, which also tells us right off the get-go that there are no net forces. The net forces are 0. There is no acceleration. And then it tells us that there's a 20 Newton force being applied to move it across the floor. So F app equals 20 Newtons. So we got all that information from those 4 things that were kind of highlighted in the problem statement. All right, so now what do we have to figure out? Well, we can always figure out F gravity if we know the mass. So F gravity equals mass times G, which is going to be 30 kilograms times 10 meters per second squared, which equals 300 newtons. We know that this is balanced, so F grav equals F norm, which is also 300 newtons. We also know, since it's got to be balanced, that that applied force of 20 newtons has to be equal to the friction force of 20 newtons on the left side. And we're done. We've got all of our forces figured out. We have all of our accelerations figured out, and we can move on. Okay, so let's look at an example where we have vertical motion. So we've got a 5 kilogram box. It's dropped from the top of a very tall building, moving at constant velocity. Label or draw a free body diagram, label your forces, calculate all the individual forces, the net forces, and the accelerations. Okay, so it's 5 kilograms, so let's write that in our box. We still have the force of gravity acting downwards. This time, since it's moving through the air, we're going to have an air resistance force, so force due to air. And it's moving at constant velocity, so that tells us that our net forces and our accelerations are going to be 0 in all x and y directions. Okay, so we're going to do the same thing we've done previously. F gravity, we can calculate it because we know the mass, so it's going to be 5 kilograms times 10 meters per second squared. So that's going to be 50 newtons. So our force of gravity equals 50 newtons. Since it's balanced, our force of air is going to also equal 50 newtons. Okay, just like previously when we looked at the end of our at rest, do you notice all of these things that are 0 over there all on the side? So again, if you really see one of these problems and you're really stuck as to what to do, You can always start with these couple of things, saying that it's balanced. So you've got your net forces and your accelerations being 0. And then the next easiest step to always do is see if you can figure out what the force of gravity is by knowing the mass. Okay, in the next video, I will go over the constant acceleration, and those add in a little bit, one more step of complexity.